Welcome everybody to the very last talk. I'm a new assistant professor at Howard University, and I'm glad to all the people that went before me. That's literally my research area and my whole entire trajectory to this point. So that's good. So today I'll be going over kind of how the synthesis of the talks that was previous, looking at biomass burning and how that can impact different cities from the West Coast as well as prescribed burning from the Midwest, and how those can also impact human health. And I've had a myriad of collaborators over the years from different institutions and governmental agencies, private industry, as well as universities. So I kind of just want to list those folks there. Anyways, so some of my work has gone over many different recent advantages that we've had in this area, recent advances. So I want to kind of look at my work at the EPA, where we did kind of totality of different impact zones or regions, what we call them, that are wildfire impacts. So the cool thing we did with this study, we ran a computational model that looked at pollution, which is CMAQ. And what CMAQ you can do, you can kind of brute force zero out the impacts that aren't wildfire related. So we did a model that had fire in it, and a model that didn't have fire in it. And we did a 5-year study. And essentially with that, once you zero out all of the other like power generation sectors, power plants, cars, all those type of things, you can look at the areas that are purely only impacted by wildfires. So on the West Coast, of course, what we expect, you can see the whole West Coast corridor from Oregon up to Washington, that there's a huge impact that you see year to year over this 5-year time period synthesis that happens all the time. And that depends on which year. Like for example, 2008, we had a huge wildfire outbreak, and that's kind of why that looks like a huge issue over the Bay Area. But there's typically always some type of fire in that region. And then other regions pop up, which is kind of cool. You see the Minnesota kind of Timberwolf area, which I call it Timberwolf area, but that's the Timberwolves up there. And then you have Louisiana, which is a lot of prescribed burning down there as well for sugarcane burning. It's a huge issue down there. And the reason why these areas are cool to see in this way is because they're really difficult to see with satellites, because you have the sun glint issues as well as issues with the water being that close. So you can't always get the full issue. Prescribed burning, you can't always get the text record. And then of course we have the Southeast, where you have the Florida-Georgia border, which has a lot of issues as well, burning with prescribed burning, because that's traditionally how people deal with those fields there. And then a lot of areas that I tend to study is the Kansas, Oklahoma border, which is the Flint Hills region. So there's a lot of prescribed burning there. It's almost like 1.2 million acres per year or so that's burning there. So that's a huge energy source that usually goes unaccounted for in a lot of different sources. So what I've seen here is that if you look at biomass burning alone, it increases the PM by about a factor of 4 in terms of what is already in our atmosphere. And then for ozone, it's about 14%. So these are things that can impact your national ambient air quality standards, as some people said before. And these are things that cities and states get blamed for that aren't necessarily their fault. So we call them non-controllable ozone sources, more or less. So if you do an air quality assessment or exceptional events demonstration, you can kind of say, hey, this wasn't our fault. It was a wildfire here or there. And you can prove it with some of these high splits, flex part models that show, okay, there was a wildfire event that happened in California. That's why in the New Yorks and all the other studies you saw, we can say, this wasn't our fault. Do not sue us. And I come from the EPA. We used to go out there a lot of people. Anyways, yeah. So you can get an increase of about 10 to 80 parts per billion of ozone or PM in some of those cases. And then now, so that study was extended for a 10-year period of time to kind of see what you can look at. And the trends kind of similar. So we showed that in the United States, prescribed burning is relatively constant. However, depending on the year, La Nina versus El Nino, where there's a wet, dry season, the tunes can change, but it's still the most variable as opposed to wildfires, where you use the large flare-ups. But prescribed burning is pretty constant, and it's usually a lot more burning in terms of acreage than wildfires, so it usually gets all the blunder because of the news. So we have to look at both of them quite equally. Now, when it comes to health, we have to look at who's being impacted. So about 30 million folks are being impacted per year. So about 10% of our population is already exposed to unhealthy air quality situations. And this is something that's homeless-wide and something that a lot of people have to take account for as we expect wildfires to grow and not going anywhere anytime soon. So these things expecting to get a lot worse than they are now, because we haven't really even added the West Coast prescribed burning, because that's still something that they're arguing about in the government level, because the folks there haven't really taken into account yet. The people aren't used to it, even though that's historically what was done for the last 100 years or so. It's been kind of teased out but now they're bringing it back in because you see the mega fires that's coming out. And we need to mitigate those things. So on the West Coast in particular, you have about 30% of the population that's living in an area that's predisposed to negative health effects before you add fire pollution to that. So that is something that we call at-risk folks who can be underserved communities, that can be communities that may be affluent, and it kind of affects all of us equally. However, there's not much that we can do necessarily to mitigate those things other than let those people know you live in these areas. Here's something you can do to, like HEPA filters you can add on your house, or you can move when there's bad issues. But a lot of people in underserved communities can't just take a 2-month vacation to go somewhere else. For example, when hurricanes were coming to the East Coast, a lot of me and my colleagues, we just left and went home or somewhere else on vacation to avoid hurricanes. Everyone can't just do that. So similar with wildfires, right? So in the Midwest, this issue of the wildland-urban interface is kind of iffy, because if you live close to a prescribed burn field, or a field that typically burns, or you have a neighbor who burns things in the backyard, now you're in that interface, as opposed to someone who lives maybe a couple miles down the road who doesn't have that same impact. So trying to quantify that and how to determine where those areas are is really difficult. And that's what I'm working on right now, trying to think about how can we quantify and say, you're in the urban interface when it comes to wildland fires, or just prescribed burning when this person is not. How do you tease out those regions? As it can be hard to model if you have so many sparse areas or different pieces and pockets. So that's something that we have to work through. And then, okay, so one of the things that from a climate change perspective, why this is important is pollution affects plants before it affects humans. So a lot of people mention the EPA standards. These are their standards for humans, but standards for plants are a lot lower. So at 70 parts per billion, or 65 parts, depending on which health air quality scientist you talk to, is when ozone affects human, our lungs, and it screws us up. But at 40 parts per billion, that's when you can start seeing impacts to different plants. So a lot of these crops you rely on, like corn, soybean, you have all types of these different crops that we rely on all our products, things that we use. These things, they reduce their ability to grow, their ability to fruit out, their ability to reproduce at that level, at a 40 parts per billion. And the problem with that is that our background in a lot of the Midwest is already sitting at about 55 during the summertime. So when they're already growing in situations that aren't healthy for them. So one study that we did in St. Louis was we looked at this trend in the air. So the background air is actually getting dirtier, but the big days where we looked at all of these exceptional events and things like that, that's getting better. So a lot of times there's a misconception of what is actually happening. Time to go, right? Yeah. So yeah, I can count to you though. Yeah. So there's a huge misconception of where the actual air quality is. So the problem is that the top tier, the dirty air, is getting better. The bottom tier, which we breathe typically every day, no matter what the situation is getting worse. So we have to figure out ways to mitigate that. And then one of the things I always like to call out is that our Black fellows, and Latinx, and Native American communities tend to be the more impacted communities. So we can see impacts where there's up to 50% greater risk in a lot of different areas. So this is something that is very close still what we have to pay attention to. So kind of what my colleagues were showing earlier, many students were showing, is that when you put this into a weather context, you can see different systems that create situations where pollution can be mitigated and transferred around the United States. So there's a huge high pressure system that tends to happen every year that just sits kind of over the Central Plains. And this is one of the mechanisms that happened to bring a lot of the wildfire pollution to the Midwest and to the East. And this situation, it kind of sits for about a couple weeks at a time. And that high pressure system just cooks and it keeps anything from getting inside of it and just sends the pollution up to Canada and back down. So we measure this with satellites as well as planes and all types of things. So I'll keep moving forward. And then also something else you have to know is part of the non-controllable ozone sources is the stratosphere. Stratosphere, it's where most of the ozone that we call good ozone sits, but there's mechanisms that can suck that down from the stratosphere and cause an intrusion that hits the surface. So if you have a frontal passage that comes through, it brings down a lot of this ozone air also. So that is another source of ozone that can be at your surface. Yeah. So some of the cool ways you can measure that is with ozone sondes. So we can launch these little weather balloons up. And we did an experiment that was in September and in August in St. Louis. So about 28 ozone sondes, and you can see kind of this cool map of all those things plotted next to each other. And you can tell like some of this is from the stratosphere and then some of this from the biomass burning. And there's different ways you can track the air based off what's in it. So the stratospheric air tends to be extremely dry, wildfire air has a little bit of moisture in it, so 5 to 10% relative humidity versus stratospheric air, which have near 0%. So you can tease out the differences, and also you can look at the chemistry, which is inside of those things, and you can kind of tell what the difference. So what we was able to determine is that biomass burning contributes up to 80 parts per billion, as opposed to stratospheric air, which is 10 to 15. And this is in the total column. So you have this total column sitting above your atmosphere. And then there's other mechanisms that maybe the breakdown of the boundary layer that can cause it to be sucked down to the surface. And you can have that same breakdown cause the city air to be pushed up to the troposphere, which will sit the next day and it'll get cooked by the sun and then it'll get sucked back down. So it's like these negative feedback loops that you can keep seeing over the time period, especially during the summer. And then so what you can do also from there is you can determine your source attribution. So you can tell, like what we did for this particular 2-month time period, 70% of the contribution of the biomass burning smoke, 70% of the column came from the biomass burning smoke, 3% came from the Midwest, and 10% came from the Southeast. So this is all types of cool things you can do for like exceptional risk demonstrations. And then again, you can plug this into a model, CMAC again, and you can do cool things where you can play with the temporal profile. So how are these fires burning? How long are they burning? Typically, wildfire has an issue where they do this fires go to work type deal, where 6 a.m. to 6 p.m. They put in the model, they have it run a nice little curve. And we know that's not true. So we can use NASA satellites to say, what is the actual time period the fire was burning? What was it active? And then you can put that time period in. So that changes the whole entire intensity of the fire. It changes the ability for the fire to shoot plumes higher, which can create the longer range transport that you typically miss in most models. So by changing this temporal profile for 3 to 6 hours versus 12 hours, it can get huge improvements in our models. So in this particular experiment, we improved about 20%, and we improved the heights that it gets to the next. It was less than 1,000 feet off, which is pretty good for plume rise codes. As they go. So if you want to read more about that, feel free to do so in my papers. But and then one cool thing we can do is for health analysis. It's sort of like this. That's why I like the interdisciplinary part of this research, is where a lot of folks, such as us modelers, we take the ground truth from the measurement folks as that's it. But if you know measurement folks, they'll tell you there's a lot of issues with our measurements. Same as us modelers, we'll tell you there's a lot of issues with our models. But you tell a health analysis person that they don't necessarily know that. So they'll take model data as ground truth and they'll compare it to hospital visits and all these things. But it's like, no, there's a lot of errors associated with each part. So we have to take all these things into account. So look at that. How does plume rise impact your health analysis? And so what we saw here was that if you don't do the plume rise right, you can miss up to 60% of the pollution that's at the surface. So you're not even attributing the right thing to what you thought you were. To not belabor the point. Then using cool studies like high split, FlexPart, and all these other trajectory studies, you can set up LiDARs, which is what we did for different experiments, and you can kind of measure where these heights are. So you can kind of go back retrospectively and correct your models and then redo the runs, and then you get more accurate solutions. So that's kind of what I did here. And then this is kind of what led me to knowing that if you don't get that plume height right, you're going to miss up to 60% more of the pollution transport. Because when I originally ran this model, looking at pollution over St. Louis and trying to figure out where that came from, without that pollution getting out of the boundary layer from those fires, it showed almost no impact to St. Louis at all. But once you get the proper heights and you look at the actual data set, and you get that height above the boundary layer that got injected, then you can see the impacts. And also, that's why I harped on earlier, the mechanism to get it back down to the surface, because a lot of it sits above. But you need those frontal passages, you need those different like cutoff lows and those wave breaks that can suck it back down to the surface. And so you have to show that connectivity between how it got there and where it came from. So next, moving on, this is another piece that I'll kind of briefly go through, is that the mortality rates from the smoke is really getting to be an issue now, because we're sitting in essentially some type of pollution at all times. And then you add a little bit to that, and you kind of push us above the edge. And what we noticed is that mortality rates due to fires is increasing about 47%. So this is a huge issue that, again, it's not going anywhere. It's something that we have to take into account. And so, with that, this will be my concluding slide. And this is kind of just some suggestions that I've made for how we can improve these things. And that's just some of the things the models don't do. A lot of people assume that they calculate plume rise for all different fires, and a lot of times they don't, because it's computationally expensive. So we need to start doing that more often. We don't need to skip over some fires, and we need, like agricultural fires, they tend to just say they're in the bottom of the model layer. that's the bottom 20 meters. So the bottom 20 meters of the model layer doesn't give you that upward trajectory. They just say it's mixed, and a lot of times that well-mixed atmosphere in the model doesn't equate to what actually is in the real world. And then the other thing is the temporal profile. A lot of models, they just assume this fire goes to work thing. And that is not giving us the proper intensity of these fires, and especially these mega fires that are shooting clouds well into the stratosphere, such as Australian fires, the Canadian fires that just kind of propagate around the whole globe. So this is something we need to account for as well. So we can do that by doing satellite data sets, we can integrate LiDAR data sets, and we can start to improve these things. Looking at the temporal profile. So with that, thanks for listening.
Thanks so much. Any questions?
Yeah.
What's the basis of your mortality data? Like, due to like mortality from fire? Like, what did it range or what did it
Like
cover?
what all the way down, like it was mostly just like longer course, like health in terms of
Like respiratory?
Yeah, it was mostly
Due to fire inhalation or smoke?
it was smoke inhalation. So yeah, it's really hard to tease out fully how they said what was what. And that's the biggest issue too.
That's
It's like how do you know what really killed someone?
Because like, it can also exacerbate cardiovascular.
And that's a big issue too. Like how do you attribute that?
Mhm.
And then the overtime killing of someone. Like how do you know what really got you? Or if you're of old age,
Yeah,
or if you have
like,
other
short-term, long-term effects.
Or if you're like me, you have asthma, it's like, what if you have an asthmatic attack? How do I know 100% it wasn't you doing working outside or was it conditions of outside that you're breathing? Right? If you got overly excited or if you already had pre-existing conditions, like no one knows really does it. So trying to figure out the hospitalization data sets, it's very difficult. I'm not a health scientist, I don't know.
All right. Thank you, Dr. Wilkins. Thank you so much for that.